So what happens? So like this. So you take a dielectric and you put it in. Does the energy stored in that capacitor increase or does it decrease? Does the energy increase or decrease? Now, the original energy, before I brought it in, potential energy original was what? It had a 9-volt battery attached to it, right? So I could use which version of the energy formula? Is equal to half CV squared, right? Since I know that it's connected to a 9-volt battery, the V is already given. The battery is going to maintain 9 volts between the plates. So I should use the half CV squared. So the original energy is 81 divided by 2 times its capacitance C. Okay? How about the new energy? Well, since the battery is connected, the voltage of the capacitor is still going to be 9 volts. So I can still use this version. Except the capacitance is going to change, right? By a factor of kappa. Okay? So it's going to be 981 over 2 C nu. By the way, let's just take a 1 minute break from this. Go over to that other table and talk about the dielectric constant of different materials so that you'll have a little bit of an idea. There's a table here in the book. It tells us the dielectric constant of different materials. K dielectric constant of air 1,00059. So pretty much the same as vacuum. Okay, the air is a little bit polarizable, but not as much as any other material. And then you can have K. Then you have other materials there. Quartz. .78 rubber. 6.7 paper. So you could put paper in there, and that's a dielectric material. .7. You see? So think of it this way. The bigger the number is, the more the molecule is polarizable and the more it fights against the electric field of the original place. Polystyrene, which is what we did in the lab, right? .56. But we didn't actually get to 0.56. We got something a little less than that, right? Some groups got 2.2. And let's see here. What's the biggest one? Strontium titanite. Okay. Titanate, 233. So very polarizable, and it really will increase the capacitance capacitor. And then water, they even give water as an example, is going to be 2.1. No, sorry, not. I was looking at something else. It's 80. water is a pretty good electric material too. But you could just simply water. Now there is also the next column next. What does that column say? Dielectric what? Dielectric strength. What does that mean? Well, on the bottom it explains. Dielectric strength equals the maximum electric field that can exist in a dielectric without electrical breakdown. These values depend strongly on the presence of impurities and flaws in the materials. So the dielectric strength tells you don't put more than this much amount of electric field, otherwise the insulating dielectric will now even conduct electricity. There's going to be electrical breakdown, and it's going to conduct electrical flow, and the capacitor will no longer act as a capacitor. So some of them, like they have the dielectric strength 3, like air has 3 volts per meter. That's the strongest electric field that you could have in there. Fused quartz is 8, mylar is 7, 12, 14, 16, 11, 24. Oh, but it's in units of 10 to the 6th megavolts per meter, so megavolts per meter. Okay? And water and vacuum have no dielectric breakdown. Have it's vacuum and water, it's missing. So water, you can put as much electric field, it will still continue to act as an insulating material. Okay, so now we have a little idea. Let's come back here and see what happened to this. So let's say we brought in, let's just say we brought in some water. We put water in there. Okay. So we brought in water. So what happens? The potential energy C nu is going to be greater by a factor of what? Look at the kappa of water, 80 watt. So the potential energy is going to be C or of vacuum times D. So if I were to put water in there, its energy will go up. Okay? So do systems like their potential energy going higher, or do they fight against that? Yeah, things usually like to do what? They like to have their potential energy go down, right? So if I let go of a bottle of water, what does it want to do? Yeah, always systems like to have their potential energy going down. So this one, the potential energy stored in it is going to go up. So is it going to be easy to put the water? Well, in the case of the water, it might be easy because I can just simply raise this vertically, open it, and pour the water. Okay? But if it was some other kind of material that I was trying to stick in there, I'm going to feel some resistive force. It's going to try to resist me. I'm going to have to do work. So let's say it was fused quartz or something, or rubber. Let's say I had a piece of rubber trying to stick it in. It's not going to want me to stick it in. It's going to resist it, so I'm going to have to apply force to it because I'm increasing its energy. Okay? How about the scenario 2? Scenario 2 is I have a 9-volt battery. I connect it. I charge it up. But then I disconnect the 9-volt battery. Disconnect it. And now place the insulating material in it. Rubber or whatever it is. So you have the cylinder, the capacitor itself, and now you're putting in an insulating material. Is its energy going to go down or up? So is it going to want me to put it, or is it going to fight against it? Okay? So which formula should I use? Well, this one, I can no longer say that it's got 9 volts on it, right? The